In lecture 8.4, we're going to take this linear graph model that we developed in the previous lecture of the hydroelectric dam and deriving a state space model for it. And it's actually fully worked out. All the details are given here. But let's just take a look at a couple aspects in particular. So the first is that let's take a look. Remember, this is our turbine, right? So the turbine is going to relate the torque on the mechanical side to the volumetric flow rate on the fluid side. And it's going to relate the angular velocity on the mechanical side to the pressure on the fluid side. And the equations are given here. And this comes down to understanding the detailed fluid dynamics of what happens when you flow fluid past some obstruction. And you may have been introduced to the concept of lift that can happen when you flow fluid over something. That sort of thing can happen on a blade that you put out in there, and if you have them arranged in a particular way with a particular profile, it creates a nice torque. And the speed of the flow, the volumetric flow rate of the flow, is directly related to how much torque you get out of it. And if you understand that, then you'll understand that there will be some relationship between the torque and the flow rate, and therefore there will be some relationship between the angular velocity and the pressure drop across the turbine as well. Now, that is to sort of hand wave over a lot of details, right? I mean, like, that takes an entire fluids class probably to understand, and probably more. But it's at least giving you kind of an idea. Remember, for each of these transducer elements, we have to go back to sort of first principles, like how does the one energy domain interact with the other energy domain? Like, how does the mechanical domain interact with this thermal domain, or how does the electrical domain interact with the mechanical domain? Remember, we did this in detail with the motors in the mechatronics course. We looked at, okay, you have a loop of wire that goes through, and then if you run current through it, it creates this torque, and that's what governs this relationship between torque and current, the electromechanical interaction there. And if you have the through variables relating, we discussed how that's called, through variables relating and cross variables relating directly, how that's called a transformer type of transducer, and how if you have the through variable related to an across variable and vice versa, that's called a gyrator. You are going to have, I believe there's a homework problem. There's a piston cylinder in your homework, isn't there? Isn't there? I thought there was. Maybe there's not. Well, a piston cylinder is actually a gyrator. It's one of the few. There are a lot more transformer examples in the world than there are gyrator examples, but there are a few. Piston cylinder is one of them. Because you relate a pressure on one side, which is an across variable, to a force, which is a through variable. So that's the piston cylinder. Pretty cool. I'm so popular right now. I have no idea why. I'm getting like all of these messages. Maybe I won something. You guys think I won something? That'd be cool. Okay, so turbine. So it's a transformer. So. And then the generator is also a transformer. So we need to do the normal tree. So the normal tree, let's work the normal tree out. We've got 3 sources, 2 of which are cross variable sources. So we select those to be in our normal tree. We have several A-type energy storage elements, C1, C2, C3, and J. So we have 4 of those. And then we've got, as far as our transducing elements, there are 4 possibilities, right? There are 2 different transducers, so they both happen to be transformers. So we have to take one or the other of each of them. So we've got 4 possibilities. But there's an easy way to determine which ones are possible. There's only one possibility in this case. Remember, we have to choose them to minimize the number of t-types in the normal tree typically, but in this case we only have one option. Can you choose 2 to be in the normal tree? No, because you create a loop, right? And can you choose 3? Yeah. Well, if you choose 3, it would be a loop with J2. So you can't choose 2 and you can't choose 3. So you have to choose 1 and you have to choose 4. So that's nice. It works out. And then we can choose D types until we can't choose any more without creating a loop. So D types, D types. We can't choose R4, so we chose R1, 2, and 3, but R4 would create a loop if we selected it. We can't select B because it would create a loop if we selected it. And now we're down to L1 and L2 as possibilities, both of which would create a loop if we selected it. Remember, these 2 grounds are connected, so that's the loop here. Okay, so there's our normal tree. And then we could go about selecting our primary variables, which are, of course, across variables on branches. Branches being elements in the normal tree, and through variables on links being elements not in the normal tree, and secondary variables being exactly the opposite, through variables on branches and across variables on links. Yeah, said that correctly. Amazing. And then we could select the state variables to be the A-type branches, the across variables of A-type branches, and the through variables of T-type links, which gives us 6 variables. So the pressure across C1, pressure across C2, flow rate through L1, the inertance, the angular velocity of the shaft of the generator, the current through the electrical side of the generator, and the voltage. Yeah, voltage of capacitors. Oh yeah, that was the battery. There's a battery as well. So, and then we've got the input vector there. We could go through our elemental equations, which there are several. I listed them out for you. If you guys find a mistake in this derivation, let me know. I did this by hand. And continuity and compatibility equations are given there. Of course, one for each passive element. And then the state equation, I actually did not do that part by hand. I used the Mathematica version of the statement package. And that's on this website. Nobody has, so I did the Mathematica version, like I said, but there, if somebody wants to translate this over into the website syntax and save an example and send it to me, there are still bonus points to be had for that. So let me know if anybody does it. So yeah, so I did that, and it popped out with this A and this B matrix. And I'm off to the races. 6th order system, no problem. Electrical, mechanical, fluid system, no problem. Right? I mean, this probably took me like an hour or 2 to work out the details and type it in, but not that bad considering it's like this huge system. So, and the difficult part, the only real difficult part after that is to estimate the parameters there. So, like we said, oh well, the intake's going to have a resistance associated with it. Great, but like what is that? Like how much resistance? What's the actual quantitative value of resistance? That's something that you need either a theoretical prediction for, which you can come up with to some extent. But for a complicated shaped screen, it's going to be hard to come up with a resistance value of it from theory. Maybe somebody's written a paper on it, and you can like find their paper description of like, okay, if it's this mesh size, then this is how much resistance is across it. You might be able to find something like that out there. If you can't, though, which is often the case, you have a situation where you don't have that, you have to do some measurements yourself. And you can, for instance, put a pressure measurement device on one side of the screen and the pressure measurement device on the other side of the screen, and also measure what the flow rate is that's going through the screen. If you measure those, the ratio of those is going to be the resistance. So that would be a way to estimate what your resistance is going through the screen. And that type of measurement is something that this is why the ME315 class is somewhat coupled to this class, or it was the mechatronics class, but then sort of continuing on to this, because you need to be able to measure a lot of these parameters and understanding how to do like a linear regression and figure out what your confidence is for a given parameter. Those are all pretty important ideas. So, yeah. Any questions? All right. See you guys on Friday then. Liam's bringing the snacks.